Okay, here's another example. Show that for any choice of the constants c1 and c2, the function phi of x equals c1 e to the power negative x plus c2 e to the power 2x is an explicit solution to the linear differential equation y double prime minus y prime minus 2y equals 0. Now notice we need the function itself, its derivative, and its second derivative. So let's start out with our function phi of x, which equals c1 e to the power negative x plus c2 e to the power 2x. And then let's take a look at, so that's the function itself, that's the y. And now let's take a look at the derivative, the y prime. So we need to take a look at phi prime of x equals derivative of this. The derivative of the exponential function is itself, but because of a chain rule, we get a negative c1 e to the power negative x, and then the 2 moves to the front, so we have plus 2 c2 e to the power 2x. And then the second derivative that we need, the y double prime, we get that phi double prime of x equals derivative of this. So we have c1 e to the power negative x, and then we get another 2, so that's plus 4 c2 e to the power 2x. So now let's put all of that together, and we have c1 e to the power negative x plus 4 c2 e to the power 2x, and then we have minus the y prime. So we have minus negative c1 e to the power negative x plus 2c2 e to the power 2x, and then minus 2 times the y, so the original function c1 e to the power negative x plus c2 e to the power 2x. And we're asking ourselves, is that equal to 0? Okay, so that's a little bit of bookkeeping here. We have the c1 and a minus minus, so that's, we have c1 plus c1 and then minus 2 c1 times e to the power negative x, right? And then if we look at all the e to the power 2x, we also have plus 4c2 minus 2c2 and then minus 2 times c2 e to the power 2x. Is that identically equal to 0? Well, c1 plus c2 minus 2c1, that's clearly 0. And then the 4c2 minus 2c2 minus 2c2, that's 0 too. So the left-hand side is identically equal to 0, and the right-hand side is equal to 0. And since the exponential function is defined for all real numbers, we can say that this is a valid solution on negative infinity to infinity. So what this problem illustrates is that we don't just have one solution for this problem, but because C1 and C2 can be anything, we can choose C1 to be 3 and C2 to be negative pi. We have infinitely many solutions to this differential equation. So how do we make sure that we get a unique solution to a differential equation? Well, we will need a few more conditions to make sure that we don't end up with infinitely many solutions. We'll talk about that later. Now, in many cases, it is not possible to find an explicit solution to a differential equation. And here's a definition of what it means to find an implicit solution to an equation. So relation g of x comma y equals 0 is said to be an implicit solution to the equation 1 on the interval I if it defines one or more explicit solutions on the interval I. So let me remind you of what does this mean when you have a relation g of x comma y. Think about the unit circle. The unit circle is x squared plus y squared equals 1. This is a relation between x and y, and it defines the unit circle in the xy plane. Now, we can solve this equation for y by subtracting x squared on both sides, and then to get y by itself, we use the square root. However, that's not the only solution. That's not the only solution. Because we can take the positive or the negative square root, and then we have two different solutions. In fact, there are many others, but that's not what we're interested in. So let me show you. This is the unit circle. And then the plus and the minus. The positive solution corresponds to the top half of the unit circle, and the minus is the bottom half. So this is the top and bottom half of the unit circle. So we have this relation here, and it defines two functions. It actually defines more functions, but it defines these two functions. Remember, for something to be a function, it needs to satisfy the horizontal line test, which the circle does not, but the top half of the circle and the bottom half of the circle do satisfy that. So let's see how that works in an example. So what we want to show is that x plus y plus e to the power xy equals 0 is an implicit solution to the nonlinear equation 1 plus x times e to the power xy dy dx plus 1 plus y times e to the power xy. Now, assume that this equation implicitly defines y as a differentiable function of x, so that y equals a function of x. What we're going to do is we're going to use implicit differentiation on this equation. So remember what we do. We start out with x plus y plus e to the power xy, and then that is equal to 0. And we're going to take the derivative with respect to x on both sides. So that's what implicit differentiation does. And let's split this up. So we get the derivative of a sum is the sum of the derivatives. So I'm going to split this up into 3 derivatives plus d dx of, and then on the right hand side we can go ahead and say that is equal to 0, right? So we have d dx of x, d dx of y, and then d dx of e to the power xy. Now the derivative of x with respect to x, that's 1. And then derivative of y with respect to x, we can write dy dx. Or you can write y prime if you prefer that. Now, this one's a little bit more tricky. The derivative of an exponential function is the exponential function itself, but the chain rule tells us that we have to take the derivative of what's inside of the exponential function. And so what's inside of the exponential function, that's the xy. And so that equals 0. So in this step, to go from here to here, we use the chain rule. Okay, so let's take a look at this now. So we have 1 plus dy dx, and then plus e to the power x y. And now look at this inside. We have x times y. So we have a product here. That means that we have to use the product rule. And so we get d dx of x, and then times y, and then we have x times d dx of y. Okay, so let's fill that out. So it's the derivative of x times y plus x times the derivative of y. All of that times e to the power xy, and that's still 0. So let's write down that we use the product rule here. Okay, let's simplify that a bit more. So now we have 1 plus dy dx plus e to the power xy. Derivative of x is just 1, so that's 1 times y, and then plus x times derivative of y is dy dx. So we have 1 times dy dx. And that equals 0. Okay, now let's simplify this a little bit by multiplying this out. So we get 1 plus dy dx plus y times e to the power xy, and then plus x dy dx e to the power xy equals 0. And let's combine the two terms with the dy dx. So I have 1 plus y e to the power xy, and then plus 1, the 1 in front of here, and then plus x times e to the power xy times dy dx, and that equals 0. Now let's take a good look at this equation, the derivative of our original function, and compare it with the differential equation here. And what we see is that this equation is exactly equal to this. So note that this is equal. And that means that our implicit function is a solution to this differential equation.